Welcome back. This is section 5.4 of Timberlake chemistry, and today we're talking about drawing orbital diagrams and writing electron configurations. So this is totally weird. You've never seen anything like this, but it's not, I wouldn't call it hard. Lots of people get this. Year after year after year, lots of people get this. I think you'll be fine, but it is weird and it's unlike anything you've done before. Let me do a little bit of reminding you that you have a period, and on that period it's essentially a shell of electrons. And a shell of electrons is a general region in space where you're going to find electrons residing. Okay, so it's an area of probability explained by a ridiculously long and hard math problem. Okay, so where is it likely that I'll find an electron? Remember, the electrons are all negative. Their charges repel each other. They're trying to stay away from each other. They're all going at about the speed of light in a big whir like a cloud. So for that reason, there's some hard things to try to understand. So these ideas of where something is a schematic. It's an idea. It's a probable region. Okay. Now the subshells, if you remember that the first shell of electrons has one subshell, and it's an S. If you're going to have the second shell of electrons would have two subshells, an S and a P. The third would have three, S, P, and D. The fourth shell would have four, S, P, D, and F. And we'll see that those four subshells is all that we need to describe perfectly the 118 different types of matter that are known. Okay, so within a subshell, you also have orbitals. So you have regions of space broken down into increasingly smaller pieces. The last piece is called the orbital, and the orbital I described as a room, a dormitory for two college girls that hate each other. They have to live together, but they don't like each other. They want to stay as far away from each other as possible. So what you see here are three orbitals. You have a 1s orbital, and you've got an arrow pointing up and an arrow pointing down. Those are representing electrons. So you have if you have two electrons inside an orbital, one is going to spin clockwise, the other is going to spin counterclockwise, and those are depicted by an up arrow and a down arrow. So the one shell is full because the first shell only has an S subshell, and that S subshell only has one orbital. The P, remember, is that second subshell, and it has three orbitals. Then you have the D subshell, it has 5 orbitals, and then you have the F subshell, and it has 7 orbitals. Okay, so in this case, we've got 1s, 2, because it's full, 2s, 2, and 2p, 2. All right, well, 1s1 is hydrogen, 1s2 is helium, so we've filled the first row is finished. Then we have lithium, that's 2s1, beryllium, that's 2s2. Then we have borons, that's the first up arrow in 2p, and then we have carbon, 1, 2, 3, 4, 5, 6. So carbon is atomic number 6. This is carbon. Okay, so we see a few things. We see that you fill the cheap rooms before you fill the more expensive rooms. And in the case of the 2p orbital, there's 3 orbitals in the p subshell. There are 3 rooms that cost the same money. For that reason, you don't have to pack them. So you don't do boron and then carbon in the same room and then go into nitrogen. If there are a room available at the same price, each girl gets her own room. Okay, so in the case of boron got its own room, and then carbon doesn't have to be boron's roommate. Carbon gets its own room. And then the next electron will fill into that third room, and then when all that subshell has 1 in it, then it comes back and each get a roommate until the P subshell is full. Okay? So the energy levels fill with electron in increasing energy. So it starts with the first shell, that's the 1s, then it moves to the 2s, then it moves to the 3s, so it's moving in increasing energy. And then it always does the subshells in the same energy way. So S's are filled first because that's the cheap rooms, and then the P's, that's the next expensive, then the D's, and then the F's. Okay, always in that order. So this is an energy diagram. So what does it, this is the price of the room. So the cheapest room in the hotel is the 1S room. The 1S room has 2 beds in it, so there's 2 electrons can be there. If that room is full, so if we have helium and now we have 1 more electron, it's the lithium electron, it has to go into the 2S. Okay, then it has 1 more, that's the 2S2, that's beryllium. Then anything past beryllium has to move into the 2P, and you have 3 rooms, so that's 6 electrons can fit in the 2P. Anything after that's the 3S, and then the 3P and the 4S, and it moves up that way. Okay, I'd like you to also see that after the 4S, the next cheapest room is the 3D subshell. Remember, there are 5 rooms, 10 girls. That's scandium through zinc. So the next cheapest room after 3P is 4S. Then the next cheapest room after 4S is 3D. So the D subshells are not in the 3rd row. The 3D subshell is in the 4th row because the 4S is actually cheaper than the 3D. And it's cheaper energy-wise, and so it'll always go into the cheapest room. If you look, there is a pattern here. You go from 1S to 2S, then 2P to 3S, then 3P to 4S, then you go 3D, 4P, 5S, 4D, 5P, 6S, and then after the 6th row, you're coming to the 4F. So the D subshell is 1 behind. It's on the 4th row in the periodic table, but it's actually depicting the 3rd shell. The 4F is in the 4th shell of electrons, but you don't see that electron until you get to the 6th row of the periodic table. So there is a pattern here, but you would have to study it for it to make some sense to you. So the orbital diagrams, this is more review of what we just said, is a room that has 2 electrons in it. It's a region of space. So if you're going to have atomic number 3, you would have to fill the 1S. So it's 1S2, it's completely full. Then the 2S1. And you call it 1 because I've got 1 electron in it, or 2S2 because I have 2 electrons in it. It tells me just by hearing whether it's full or not full. So electrons in an atom fill each in a subwell until it's half full. Okay, now the S is the only subshell in that, then the subshell is full with that 1 orbital, so it gets a roommate automatically. But when you get to P's and D's and F's, everybody gets its own room. Then you come back and do roommates. So in the case of a P where there's 6 electrons, you'll do the first electron gets a room, second gets a room, third gets a room. Then the 4th electron in that 6 goes back and shares with the first guy, and then shares with the second guy, shares with the third guy. So let's look at nitrogen. Nitrogen is 1s2, 2s2, 2p3. Okay, that's nitrogen. Well, once you get to nitrogen, remember you had boron, carbon, nitrogen. Boron was the first room, then carbon each got a room, and then nitrogen got a room. Now when you have oxygen, oxygen needs a roommate because there are still beds available at that cheap price. You can't go to a more expensive room until you fill the cheaper rooms. So oxygen is boron's roommate. Then fluorine is nitrogen's roommate. Okay, then neon is fluorine's roommate. And once you get to neon, that whole shell is full. And remember, neon is a noble gas, and it's full, it's stable. So the orbital diagram for carbon consists of 2 electrons in the 1s, 2 in the 2, and then 1 electron each in 2 of the p orbitals because it gets its own room. The electron configuration for carbon is based upon how many electrons are in each subshell. Look at the side. 1s2, that's hydrogen and helium, 2s2, that's lithium and beryllium, 2p2, that's carbon and nitrogen. So if you want to say, or for carbon, boron and carbon, 2p2, 2p3 would be nitrogen. So what is the orbital diagram for nitrogen? All right, so nitrogen is after carbon. So boron got its own room in P1, carbon got its own room in P2, nitrogen gets its own room in P3. So all the 1s's are full, all the 2s's are full, then there's 3 rooms, each with 1 girl in them. So nitrogen is that first one, okay? Oxygen then would come back and do a roommate, and then magnesium, all the 2's are full, and then magnesium's in group 2. That means it needs to be the next shell, 3, with the first and the second electron full. So magnesium would be 1s2, 2s2, 2p6, 3s2. The electron configuration is this big long chain of numbers that tells whether or not the rooms are full. And remember, all the rooms have to be full before the more expensive rooms are available. You always fill from lowest energy to highest energy, okay? So this would be 1s2, 2s2, 2p2, okay? So 2s2 would be beryllium, 2p1 is boron, 2p2 is carbon. Okay. In period 1, the first 2 electrons go into the 1s orbital because there's only one subshell in the first row. In the first shell, there's one subshell S, and there's one orbital in S, and so it both gets a roommate, hydrogen and helium. The abbreviated configuration shows the symbol of the noble gas in brackets. Okay, so once you start getting big, this gets really, really, really long. You could have an electron configuration that would be 6 inches long on a piece of paper. Well, that's a little bit annoying. So what you'll do is when you get to the last 2p6 or 3p6 or 4p6, whatever that noble gas configuration is, you will put that the symbol of that element in brackets. Those are the square parentheses in brackets. Then go to the next row that's not full and do the rest. That way it's shorter. It's the same information. So for instance, helium is 1s2. Then if you have fluorine, then you're going to have 1s2, 2s2, 2p, 1, 2, 3, 4, 5. Okay, so that's fluorine, 1s2, 2s2, 2p5. Well, helium is 1s2. That whole row is full at 1s2. So do helium plus 2s2, 2p5. Now in a case real small like this, in second row, it's not a big difference in length because they're practically the same length. When you start getting to 5th row, 6th row, 7th row, it's huge difference in how long you have to write this because there's 1,000 of these that you have to write. Okay, so looking at neon, okay, neon, this is all in the second row. Neon would be helium, 2s2, 2p6, and now that's full. Now we could use neon and keep going. Once we have group 8, once we have a noble gas configuration, whatever is in the next row would simply be noble gas plus whatever. Okay, so let's do argon. Argon is the noble gas configuration lower than neon. So if you want to do the whole thing, you have to do it all. 1s2, 2s2, 2p6, 3s2, 3p6. That's argon. Well, just go up 1 to the previous noble gas configuration of neon and just say neon brackets and then just keep going. 3s2, 3p6. And it does become shorter and shorter as you get bigger and bigger. Okay, so what is this? The correct electron configuration for nitrogen is, you would have to look on the periodic table. So let's pull up a periodic table. Okay, all right, so we'll just see. I don't know if you can see it well. Okay, so the first one is for nitrogen. Well, where is nitrogen? Nitrogen is here. right here. So what is that? These are all S's, these are all P's, these are all D's, these are all F's. Okay, so what do we have? Nitrogen would be 1s2, 2s2, 2p, 1, 2, 3. So 1s2, 2s2, 2p3, so it would be number 3. What about oxygen? Well, here's oxygen, so this is 2p, 1, 2, 3, 4. So it's 1s2, 2s2, 2p4, and that would be number 2. Okay? Do you see this looks confusing, but so many can catch this. This is fun even for some. Okay? If I were with you, we would play Battleship. This is a beautiful one to play Battleship, where I give you a periodic table and you go back and forth and trying to guess where people put their boats. Okay? What about calcium? Okay, so calcium is here. So it's in 4s2. So what do I need before 4s2? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, and then right after, the next one after 4s2 would be 3d1, 3d2, 3d3. So these D's are off by 1. It's a third shell electron in the 4th row of the periodic table. When we get down here to cerium, it's not until you get to group 6, but it's a 4th shell electron. So it's 2 off. It's in, you see it after 6s2, then you see 4f1. Okay, so the one for calcium would end in 4p or 4s2, so it would be number 2. Okay. Write the electron configuration and abbreviated configuration for the elements. Okay, so chlorine is 17, so you need 2 first, so 1s2. Then you need 2 again, so that's down to 4, so that's 2s2. Okay, and now you need all of 6, so it's 2p6. Now you have to keep going because we're not to. Let me put that again. Okay, so we want here, we're a chlorine. Okay, so we have 1s2, 2s2, 2p6, 3s2, 3p, 1, 2, 3, 4, 5. 1s2, 2s2, 2p6, 3s2, 3p5. How about sulfur? 3p4. How about potassium? Okay, potassium is in row 4, so it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. All right, that's a lot for you. I hope you can put your brains around this.